All right. We study continuous fields of system algebras. Well, because they occur naturally as natural examples, and also they can be used as tools, especially in K-theory. K-theory has a robust stability property, and then using continuous fields, we can produce deformations which preserve K-theory, but they are much more flexible than strict homotopy. Okay, but today I will start with very elementary examples, so that people who are not familiar with the subject will get hopefully a good feeling. All right, so what is the setup? So X would be a locally compact Hausdorff space. All right, and then by definition, so there are several definitions, possibly many, but I'll take the following. So what is a continuous field? So a continuous field of sister algebras over X, over the space X, consists, first would be a family of sister algebras, so a family of sister algebras which are parametrized by X. And then we specify a sister subalgebra of the sister algebra which is the infinite direct product, the direct product of these algebras. So we have these standard constructions, the product of a family of sister algebras, and A would be a subalgebra, sister subalgebra. Okay, and of course they need to satisfy a number of conditions, and here are conditions. So we have an element of A. If it sits here, it has coordinates belonging to these algebras, A of X, right? And we want to impose some continuity conditions, so the norm of these coordinates should be continuous. So this map should be continuous for any A in A, and in fact we want to be in vanishing at infinity. So C0 X are complex valued functions vanishing at infinity. Right? So we want the norm to vary continuously. Okay. Now we want this algebra to be A, to be rather big. So and then if we collect the coordinates for any fixed X, we should get a surjective map. So this is only for any. Okay, and then the third condition is that this algebra should be a C of X module with respect to the natural multiplication. So if f is a continuous function vanishing at infinity on X, and if A is an element of A, we want the product f times A to belong. Right, so what are the coordinates here? F of X times A of X. All right, so this is the definition. Okay, so it is not easy to absorb this definition the first time one would see it, but so let me give you first one example. Okay, so a so-called a trivial field. So I take a continuous function vanishing at infinity on the set on the space X with values in a fixed system algebra D. So here all the elements AX or the algebras AX are the same algebra fix B. And another example, you may call subtrivial fields. System algebras. So where A is a system algebra of continuous functions from X with values in B of H. You see? So should be a subalgebra of a trivial field, and of course we want this embedding to be C of X linear. So and an embedding inside domain. All right, and then here I'm in precision, so I should not talk about C of X linearity. So I can multiply elements here by function C0x, and then A should be homogeneous, so this should be equal to A. Whether or not I put a closure here doesn't matter. There is Cowan's lemma, which says that this is automatic. All right, so you can imagine, for instance, start with any C-star subalgebra of this trivial field, multiply it by C0x, and take the closure. And then you will get a continuous field, which is subtrivial.
Is there a particular reason why you take B of H instead of just any fixed algebra D?
Right, if I put D here, then would be automatically. Right, so these subtrivial fields are already very complicated, and they are rather general. So just let me mention a theorem of Etienne Blanchard and Fischberg. Which says that if A is separable exact system algebra, which is a continuous field over a space X as above, then it's subtrivial. Then A embeds in, you see, the algebra A by Fischberg theorem being separable exact embeds in O2, right? But if moreover has a continuous field structure over X, then we can embed it as a continuous field. So we embed in C of X, C0 of X is values in O2. All right, and You know, initially I should have said that the discontinuous fields, okay, but the theory was introduced by Fell, and I should mention one easy result in his many important results, which says that, let's say that A, this is not necessarily A, it's a separable C-star algebra whose primitive spectrum is Hausdorff. Okay, so then it's automatically a continuous field. X and right. I will add something more with simple fibers. Simple in the sense of system algebra. The fibers are simple. So in this definition, A of X, these elements, they are called the fibers of the continuous. Okay. So of course, C-star algebras with Hausdorff spectrum are you know, restricted in some sense, but anyway, if that happens, then okay, there will be other examples, but natural examples which I will raise in the future. The irrational rotation algebra, so the family A theta, regarded as a family depending on theta, that forms a continuous field, really is the C-star algebra of the discrete Heisenberg group H3. It's a continuous field over the circle, and the fibers are the irrational rotation algebras. So that's a classic example.
So is that one not subtrivial? Or?
It is.
So can you give us an example of something that is not subtrivial?
No. So I had a conversation with Takozo at some point, and I'm not sure if I understood well, but he saw that he had an argument which shows that actually all separable continuous fields are subtrivial.
Then you should maybe not call it subtrivial.
Right. So when you study these continuous fields, right, if you want to use them as application theory, then you are not interested in the field, in the fibers to be, or in the continuous field to be locally trivial. You want a lot of flexibility. Whereas for other applications, since continuous fields play the role of bundles in statistical algebra theory, right, you want for some nice classification results in for interesting classes of examples, which for instance will incorporate the Dixmier-Douady theory. Okay, but I want to start with some concrete examples which will illustrate the complexity of continuous fields even over the unit interval, even if all the fibers are mutually isomorphic. So, right, and now I need one more notation. So if U it's an open subset of X, right, then we can associate an ideal A of U, right, which is simply C0 U times A. And if AF is a closed subset, then A of this is an ideal. A of F is a quotient of A, and it's a quotient of A by the ideal, the complement of F. So in particular, if if you take the set X, this is closed, then right, so then A of X can be identified with this quotient. So these are the fibers. So the fibers are quotients, you know. Now, you see, in a trivial algebra, right, you have a natural map, you can evaluate at points. Okay, so this respects this structure because if you have a, you know, a C of X linear embedding, yeah, so of course, here it's C of X linear. This, all of this is compatible with the embedding, right? So maybe just to make this very concrete. So we have a commutative diagram. So let's say that we embed A. There, right? And then here you can evaluate X, B of H, and then you have this abstract evaluation, you know, if you evaluate in this way, this quotient, right? So, so this diagram, it's commutative. So really, evaluating, you know, passing to a fiber, really it's very much like evaluating at a point. The functions and evaluate functions. All right.
I have a question regarding
Yes.
the Blanchard-Gedbeck theorem. So is this embedding unique in any sense, or? I mean, could you describe, you know, this same C-star algebra in many different ways as a continuous field?
No, if one uses this Fishback, that unpublished, but in the for continuous fields, you know, the arguments are sort of clear. You know, you have some sort of uniqueness because up to asymptotic, you know, because O2 it's contractible. The same sort of uniqueness when you embed any exact separable C-star algebra embeds in O2. And there is a uniqueness up to approximate unitary equivalence. But that does not give the structure, right? So whatever structure it is, you can realize it isometrically preserving the C0X structure. Right? So, another example, I realize that okay. This is definition. So we say that A is locally trivial. If for any X in X, there is F maybe closed neighborhood of X, such that if you restrict, then this is isomorphic to continuous function of F with values in some fixed algebra or some D. You can formulate it also with open sets. You know. So locally, it looks like. All right. So that now. All right, so I want to look at several more examples. So I take this algebra A, continuous functions in 0, 1, with values in 2 by 2 matrices. These are 2 by 2 complex matrices, which have the property that F1 is scalar. So in other words, F is diagonal matrix. Right, so you can imagine, you know, that this looks like so, and 2, and here at 1/2 you drop to a subalgebra, you know, subalgebra, let's see. And I should also give an, I blame it on the jet lag, you know, that skipping certain part, right? If X is the space for each point in X, we have a fiber of X, Y, of Y, right? And with this formula is like any element A in A gives you a section in this bundle. The values here is of X, and you have some continuity property. Okay, and that's what this concept is supposed to catch. All right, so that's yeah. Now we can ask: is this field locally trivial? Okay, the answer is no, because the fibers, right? So if I'm looking at the fibers, so what are they of X? They are isomorphic to full 2 by 2 matrices. If X is not 1/2, and complex numbers, if X is 1/2. So it's not locally trivial around 1/2. Okay? So, but what if I'm looking at A tensor the compact operators? Okay, so K are the compact operators in separable Hilbert space. Okay, so we can ask, is a local trivial? Okay, and then you say, well, maybe we can look at A tensor O2, where O2 is the Kunz algebra, or maybe, okay, maybe O2 is the Kunz algebra, or we can tensor by n to infinity. So this is the Kerr algebra. So why do I mention these examples? Because these, here the fiber gets corrected. Now all fibers are abstractly mutually isomorphic. Okay, so M2, I mean, this behaves as you expect, at least, you know, in this nuclear case. M2 tensor the compacts, it's abstractly isomorphic to the compacts. C tensor the compacts, it's isomorphic to the compacts. So this happens not for any X. Okay. O2 absorbs M2. Okay. And of course, the same thing happens with the Kerr algebra. If they are locally trivial, then they should be trivial. Why? Because they are locally trivial, you know, the bundle theory, you have a bundle over a contractible space, they have to be trivial. Okay. Now, Dixmier-Douady, they studied extensively continuous fields with all fibers isomorphic to the compact operators. And for continuous fields over finite dimensional space, they gave a necessary and sufficient condition for local triviality, the so-called Fels condition. Okay, so, and then we'll see that this field will fail to satisfy Fels condition, and therefore is not locally trivial. Okay, so. So I'm a little bit vague here, you know. So fields of compacts over X finite dimensional. This means has finite dimensional covering dimension. Locally trivial if and only they satisfy Fels condition. Okay, and I'll explain that orally. So, Fels condition asks that around each point you find for each point you find an element of the continuous field, so that if you restrict that element to some small neighborhood of the point, you get a projection of rank 1. So you have local projections of rank 1. Now, rank is well defined, even these identifications of the compacts are not canonical, because, right, they need to isomorphic. The rank is reserved under automorphism of the compact, so rank is well defined, rank in a field. Right? So, in this example, right, so here this, this fails, this condition. And why is that? I will explain here, Can we find in this algebra a section which is a rank 1 projections around 1/2? So let's take such a projection, at 1/2, I have the scalar, so that projection must have to be equal to 1. Okay? But now, what will happen on a small neighborhood? On a small neighborhood, we look like would be a projection which is close to 1, 1. So therefore, we have rank 2. Okay, so you see, you cannot find such projections. And of course, this condition is necessary, because if you have an algebra of the form C01 is values in the compact operators, of course you take a constant rank 1 projection. All right. So this we know. What about those examples? Okay. So as it turns out, and I'm going to explain, they are trivial. Okay. So in fact, there is a generalized Fels conditions in terms of K-theory, which for continuous fields of Kirchberg algebras, pure infinite simple nuclear system algebras, is necessary and sufficient for spaces of which are finite dimensional and will fail for infinite dimensional spaces. So, now, in order to generalize and truly understand Fels conditions, we need some elements of K-theory, because that's the proper context. So, I'll say a few words on that. And to that purpose, I will take a small array generalizations for these examples. In order to illustrate the role of K-theory. Okay, so now fix the algebra and let's see a star monomorphism, an injective method. Okay, and let me define A to be continuous functions from 0, 1 is greater than D, where the only condition is that 1/2 we drop to a subalgebra. Now, since this is injective, right? Then of course this is isomorphic to D. D on 0, 1 at 1/2 we drop to a subalgebra. Right, so then, you see, these examples are of this type, where D, it's M2 tensor compact, or M2 tensor 2. All right, so how do we study this algebra, right? It's natural to consider the following extension. So I have A. I evaluate at 1/2, right? I take evaluation of 1/2, and then the quotient is isomorphic to this, right? So maybe I should explain. I take evaluation of 1/2. I end up in 0D, and then C inverse. This is isomorphic to D. And what is the quotient? What is the quotient? Functions on 0, 1 vanishing at 1/2, right? But this is precisely the direct sum of two cones, because the first half functions on 0, 1/2 vanishing at 1/2. So this is, it's isomorphic to the cone over D plus the cone over D. So this is the cone, functions on an interval vanishing at 1 endpoint. Moreover, let's observe that this is split. This is split. Split extension, and you see, if I have an element D, I can send it to the constant function C of D, right, and which belongs to the field. Right? So now, if I'm looking at K theory, or any homological invariants or homology to here, you see they vanish on contractible algebras, right? So it follows that K0 is based on homotopy classes of idempotents, right? So K0 of A is isomorphic to K0 of D. Right? Since K theory of the cones is 0. And moreover, since this quotient map is, this is the quotient map, it's an isomorphism, we understand completely the K theory of A if we understand the K theory of D. Because I take one element in K theory here, which is represented perhaps by idempotent, and I place that idempotent here as a constant function. Right? Now, some sense, you should think of this map as evaluation at 1/2. It's not really evaluation of 1/2. It's followed by this identification. But I'll make the following observation. If A happens to be isomorphic to the trivial field, right, then it follows that all evaluation maps from A to AX, so maybe are isomorphisms in K field. Why is that? Of course, this algebra is homotopic to this, so we go. No, it's by same argument, by the same argument. Right. If you evaluate a point, you go to D, so the kernel is sum of two points. All right. So now, let's try to verify this condition on this field. So I have A. I take this map evaluation at 1/2. Okay, so this is K0 A, K0 A1. Okay, so this is isomorphic, this is okay. And then I evaluate perhaps at point 1. So now at 0, here clearly the fiber is Z. Okay, and so now if you remember, the isomorphism is given by this split. So this is I know. Okay, so maybe I'll just write this. The map that you get here is precisely K0C. So this is the map induced on K theory. Right, because the take an idempotent here, lift it to A, the constant idempotent. But how do you lift it? Its image is phi of that idempotent, and then you project it down. Okay, so it's constant, you get C of t. So this so if this happens, right, it follows that must be a bijection. So that's a necessary condition for local triviality. So now, if I'm looking at the examples above, right? So in the first case for the compact operators, so this map, T star, I mean in all these examples, T star is multiplication by 2. Okay, so here Z goes to 2Z. For O2, K0 of O2, it's 0. I still have multiplication by 2, but this is an isomorphism. And for the car algebra, K0, it's isomorphic to Z of 1/2, right? And here, multiplication by 2, right? It's a bijection. So there is no obstruction. So here you can see the connection with Fell's condition. How you capture this ramification of the multiplicity around it. All right, so phi must be bijective. Now, so this allows us to use just one tool for continuous fields whose fibers are not necessarily compact operators, but abstract system algebras. Of course, you can repeat this reasoning for K1 now. Right, so K1, K1, and in fact, if you think of KK theory, the class of P must be an element which has paradox KK theory, it's KK vertical. Okay, so it's along the same lines. Now, okay, so if A is trivial, so once again, keep in mind, because this example it's rather general, I will explain. Right? So here you drop to a subalgebra, okay, given by an embedding, and then if this is trivial, then C has to be a KK equivalence. Now, is there more conditions than we need to truly realize this triviality? Yes, in general, of course, because this is just a topological condition. However, if D is a stable Kirchberg algebra, that's the only condition that you need for stable Kirchberg algebras. Okay, and there is. It's not a hard exercise to show the following. Okay, which answers these questions of local triviality. But okay, so this is an exercise. Right. So A, like here. So A is trivial. If and only if there is a continuous map theta from the unit interval into endomorphisms of D, such that theta of 1/2. So this is continuous. This is the point in our topology with C, and theta of x is an automorphism for any other x. See, this is the necessary and sufficient condition for triviality. Okay, it doesn't matter, that you can drop to a subalgebra as long as you can deform the embedding from the subalgebra C of D to D to continuous integrated in a one parameter family of automorphisms. And then you can, if this happens, then you can write explicitly the isomorphism. You just use this family fiber-wise to realize the isomorphism. So, if D is a Kirchberg algebra, this condition is equivalent to a purely K-theory condition. Or, moreover, if D is a Kirchberg algebra which satisfies the universal coefficient theorem, KK equivalence is the same thing as isomorphism of the K-theory. So really for UCT Hirschberg algebras, this is necessary and sufficient. Okay, so this is some progress. Namely, if you have a continuous field of Hirschberg algebra with one singularity of prescribed type, we know that its local triviality is decided by a K-theoretical condition. So the nice fact, which I'm going to explain next time, is that for spaces, for compact spaces of finite dimensional covering dimension, local triviality is purely described in terms of KK theory. And moreover, for the continuous field of Hirschberg algebras, let's start with the intervals. Any arbitrary field can be realized in some sense of as an inductive limits of fields which have finitely many singularities. Imagine a step function, constant. Then we imagine the analog continuous field of their construction, and one result is that any field of Hirschberg algebra satisfying UCT, actually on any finite dimensional compact space, is an inductive limit of these fields, which are simple fields.
You have to be able to compute the K-series of this Hirschberg algebra, right?
Yes. Right.
What do you need to know, the exact group or what?
Right, to verify, right. Otherwise, right, you need access to the object, otherwise. So here the step is that you have, this is an analytical object, a continuous field, and then you answer local triviality in terms of purely topological data. So that's now.
Sorry. What topology do you have on the end of
The point non-topology.
just one?
Yes. So now I do one more example. One I will mention briefly. Okay, so under 1 hour, this will be a missing example. So imagine you take such a field with one singularity at 1/2. Now take another field with the same fiber D, same map C, where you move the singularity around. Maybe you create one singularity at each rational point. Take the tensor product, infinite tensor product of such fields, a balanced tensor product over 0, 1. So you get a continuous field over 0, 1, where the fibers, what are the fibers? They are the infinite tensor products of D. Right, so you get a continuous field whose fibers are mutually, abstractly, mutually isomorphic over the unit interval. And then one can show that if one chooses to see carefully, so that is not a bijection on K theory, this field, whose construction I described, is not locally trivial, it's nowhere locally trivial. I mean, no matter which point you take, for some interval around that point, the field it's not trivial. Right, so the base, it's the unit interval. The fiber is a fixed, separable Hirschberg algebra. All of them mutually isomorphic, and there is no point around which the field is locally trivial. And the way you do it is with K theory. You have maps between tensor products of system algebras, and the maps are tensor products between identity and C, so you can compute the K theory. It's not an isomorphism, so this makes. Right, so even one parameter continuous fields of this fixed fiber can be awfully complicated. How to, of course, say is there any hope to classify such fields? And there are some satisfactory partial answers. The answer involves the sheaf of K-theory. So, you know, you have to look around all points. And it's, for instance, if you tensor with the universal UHF algebra, then they are completely classified by field, by a K-theory sheaf. All right, but now I want to close with another example. Okay, so E would be a continuous field over X. X would be the Hilbert cube. So it's a unitary system algebra. So E of X would be isomorphic to. Okay, and E is nowhere locally trivial. Okay, so this might look surprising. Why? Because X is contractible and O2 it's K contractible, so there is no K theory. How do you detect that this is not locally trivial? Okay, the answer is still K theory, you know, but this example shows that one has to look. It's not sufficient to inspect the fibers on the base, just because, you know, if the object is not locally trivial, you know. So I have a theorem which says that if X was finite dimensional, then this is trivial, it's C of X tensor of 2. And then in the infinite dimensional, if X is infinite dimensional, then I gave an example which shows that, you know, it cannot be achieved. And this example starts with an example of Hirschberg, Roddan, and Winkler, okay, which has, like, it's really very short. Okay, yes. So, that's an example of Hirschberg. Okay, so I'm looking at this projection P, which is 1, 0, 0, and E. Okay, this is in 3 by 3 matrices over the two sphere. And E, it's a Bott projection. Right, so E, it's in 2 by 2 matrices. But this is a rank, this is a rank 2 projection. It's a rank 2 projection. And then I consider algebra B. I compress C by 3 matrices. I take the corner. And they took the corner, right? Okay, so this is a continuous field over S2, and the fiber is 2 by 2 matrices because the projection has rank 1, so P has rank 2. Okay, and then A, I will take the infinite tensor product of B with itself. Okay, so right. So this is not a balanced tensor product. So this is a continuous field over the infinite product of spheres. And what is the fiber? Right? The fiber will be the infinite tensor products of M to C, will be M to infinity, the Car algebra. Right, and what Hirschberg, Rodham, and Winter, they noticed that they simply proved that 2 does not divide the K-theory class of the identity of A, right? In K0A. So one can compute K0, but you don't need really to compute, but one can compute, and then the class of identity is not divisible by 2. So, because of that, it shows that A is not isomorphic to the trivial field. Why? Because in the trivial field, the identity is divisible by 2. All right, so I try to understand this example and see what the ramification can have. And then one quick way to compute the K-theory is that you have a natural map from C plus C into D, and which sends 1, 0 to 1, and which sends 0, 1 to the both projection. And it turns out that this map is a K equivalence. It's a bijection on K theory, and we know the K theory of the sphere, everything. And therefore, if you take infinite tensor product, you still get a KK equivalence, but then what is the infinite tensor product of this algebra of itself is the Cantor set. So therefore you get a KK equivalence between continuous function on the Cantor set and the algebra A. So this is the KK equivalence given by this embedding. So K is Cantor set. All right. So now with this, right, you can compute the K theory of A, and then you get the continuous function. This is continuous function from the Cantor set with values in C, because the K theory is. So that's what is the K. And then the class of 1 is the constant function 1. The constant function 1. So clearly you see that it's not divisible by 2. All right, but now I want to do the fact to end up with the following observation. Right. Let's look at A tensor O3. A tensor O3. Okay. So what are the fibers? The fibers are the fibers of A tensor O3. Okay, so we need to identify this algebra. This is a Hirschberg algebra. So we compute its K theory. So it's Z1 half tensor Z mod 2. Okay, so this is 0. And K1 is also 0, so you know this in fact is isomorphic to O2. So the fibers of A tensor of 3 are all isomorphic to the same algebra O2. Okay? Now, what about the K theory? Okay, so I can use the QNet formula. There's no problem here. I get K0 of 8, I get CKZ tensor, the K theory of O3 Z mod 2, so I get continuous functions on K to reduce to Z mod 2. Okay, so let's see. I have a continuous field of O2 over the Hilbert cube, which is not trivial. Why? Because it has a K0. Okay, so there is one more trick, but I'm out of time, where you realize this is a subalgebra here. You know, there is some elementary construction. Really, the base is irrelevant. Okay, so one last sentence. What are other invariants that can detect this? So one has to look at all the ideals here. And then I have a theorem with Ralph Meyer, which says that if you have a continuous field over any compartmentalizable space, if the fiber is O2, becomes trivial after tensorization or infinity if and only if all ideals are KK contractibles. So it's not enough to look at fibers. You know. So there is this very complicated homological gluing which is hidden, you cannot see on the space or on the fiber. I apologize for looking over time. Thank you.
Questions or comments? Speaker? Let's thank the speaker again.